We already spoke about the proton-proton cycle that produces a lot of energy through fusion in stars. And now we're going to look at what happens when the stars have a larger mass than our sun, normally greater than about 1.3 times the mass of our sun. Now, if you look at this cycle, it looks as if it's just one closed loop. But when you look at it in more detail, and most places you will see this, but you need to remember that it could go different routes depending on how many nuclides we have, depending on how hot it is, depending on the luck. Is a proton hitting it at the right angle, so the orientation of the collisions, and also on the half life. These elements have all got different half lives, so there's a lot of things that can cause it to go in different ways. And we actually played a game at varsity. You can ask me if you want to play it, and I can make it for you. So you're going to have to ask me before your next lesson after you've watched this, and we can play the game, because what you'll see then is that there are some stable um, atoms and some unstable ones in this whole process. Now, what happens to the stable ones is when they get lucky, they can absorb a proton. So remember, a proton is just a hydrogen, so they can absorb a proton. And what happens when they do this is they take the proton, and then you can see the proton number is increasing, so you get 13, or the mass number is increasing, you get 13, as well as the proton number, the atomic number is increasing, and we have 7 now, which gives us nitrogen 13, which is not a stable nuclide or nucleus. Now, what happens to the unstable ones is that they will decay. So depending on their half-life, they will take their time and then they will decay. The decay means they don't take up anything, but what they are going to do is they're going to give off something. So they're going to decay through beta plus radiation, beta plus decay, I shouldn't say radiation, decay, and they will then send out a neutron which stays here. So it means that the mass number actually stays exactly the same. So it still stays 13, the mass number there, and then this becomes 6 here, and we have carbon because it became 6. So you can see what happened here is that a proton actually changed into a neutron. So the mass number stayed the same, and then that's the difference between beta positive and beta negative decay. So here we've got a carbon atom now, which is pretty stable, and but with that it sends out a positron and an electron neutrino. Now, this positron will immediately go and annihilate a normal electron, and we end up with another two gamma rays. A lot of energy in the form of photons being sent out. And now I end up with this carbon 13. Now, the carbon 13 is pretty stable. I didn't actually write it in here by the stable ones, but it is pretty stable. So we've got carbon 13, and now when it's ready and it's lucky enough, it's going to absorb a proton. So it's going to absorb one of these again, which means the mass number is going to increase. So we're going to end up with a mass number of 14. I'm just going to stick with the green, end up with a mass number of 14, and this will change because I'm adding a proton, so this will change to 7, and that is normal nitrogen. So this time it is pretty stable again. Now there's nitrogen, and you can see the chain that's already starting to happen. This nitrogen is stable, so when it gets lucky, it's going to take up a proton. The proton is then going to do the same thing again. It's going to increase the mass number to 15. The 15 and also the atomic number to 8, which you should recognize as oxygen. And there's the O in the cycle. So now we have the oxygen there. and this is not stable. So this is again not stable, and then you need to realize. So that's why it was there in the red. So not stable, and it's going to decay. When it's ready and it's reached its half-life, it's going to decay through positive beta decay again, and we're going to end up now with a nitrogen that is 15, and we're going to have 7 because the same thing that happened there is going to happen. We're going to have an electron, remember, that's going to, a positron that's going to be annihilated by an electron, and again, gamma radiation. Now, oh, I didn't write what this is, but you should recognize by now that if it's 7, then it is again nitrogen. Now, in that, what could be the last step is that this nitrogen that is now 15 as a mass number could again absorb a proton. So again it absorbs a proton, and then that's going to form carbon 12 for us. And we know already that this is quite a stable isotope of carbon. And also you can see that it brings us right back to where we started. You could start at other points and end back where you started. You also don't have to end back where you started. But here's something wrong, because remember, these must still balance. And what happens here is that we are actually going to form a heavy nucleus, which is helium, because we need to balance all these numbers out. And the helium nucleus is what is created then with the carbon, and it can go back. So now what you'll see is the carbons are still here, the nitrogens are still here, everything is actually still there. So what happened in this whole reaction is really just that we took 4 protons, so again hydrogen, we took 4 hydrogens, and what happened to those 4 hydrogens is that they combined with electrons, or not combined, but that's also what went into the reaction, and we ended up with a helium nucleus. We ended up with some neutrinos, 2 of them, and we actually have formed 7 gamma photons. And so obviously this releases lots and lots of energy. Now, remember, there are 2 units that we use for energy. We're mainly going to use joules. Joules is the one that we use, but you'll see many textbooks do still use electron volts. And as not still, it is a common unit for energy as well. So you need to be able to convert between joules and electron volts. You do this in matric in your normal syllabus as well. And that is just to change from joules to electron volts. We're going to say that 1 electron volt is equal to 1.6 times 10 to the minus 19 joules. So you could do the conversion. This whole process actually sends out 2.67 mega electron volts. So it's quite a lot of energy if you think these are just 4 particles that we're talking about, and there are millions and millions of particles that are doing this at the same time. Now, this could obviously not carry on and on forever. That would mean stars do live forever. And although they live very long, they do not sadly live forever. So they can absorb, what can happen is that the helium can be absorbed in some part of so helium, these heliums that are forming here, I didn't even write an E. This helium that's forming here could be absorbed by the oxygen or the nitrogen along the way somewhere. And they can form heavier, a more stable nuclei like F and Ne, which means they can then escape this cycle. And that's kind of how the game ends if you play the game. So they can escape the cycle and they're then out of it. And that is how stars eventually, and we're going to look at that in way more detail. So this process would not always carry on forever and ever. There would be a time, there would come a time where the star's lifetime comes to an end, sadly.